So, picture this. You are standing in the middle of this massive, just incredibly crowded, booming rock concert.
Oh, I can feel a headache already.
Right, like the bass is physically vibrating in your chest. Thousands of people are just screaming the lyrics around you, and the stage speakers are practically blowing your eardrums out.
Yeah, sounds like a nightmare.
It really is. But now imagine that you are trying to hear what one single person who is standing all the way across the stadium is whispering.
Well, yeah, I mean, that's an impossible acoustic scenario, right?
Exactly.
The sheer volume of the crowd, the background noise, the interference, it all just totally washes out that single voice. You would need, like, some kind of magic microphone to filter out hundreds of thousands of people just to isolate that one person.
Right. Well, welcome to the Deep Dive Lab, because today we are going to talk about a very strange question. How do you listen to the heartbeat, like the exact molecular vibration of a single solitary molecule without the rest of the chemical soup just drowning it out?
Which is such a fascinating question.
It is. And for a century, chemists have literally been wanting to do exactly this. And today, we have this incredible stack of sources to go through, including this really groundbreaking February 2026 research paper published in the journal Science that finally solved this mystery.
Yeah. And the mission for this deep dive is to basically explore how a team of scientists managed to invent what is essentially a molecular stethoscope.
A molecular stethoscope. I love that.
Yeah, and it works with absolute atomic precision, so it allows them to not just, hear the molecules, but to literally watch them shapeshift in real time.
Which is just wild. But, okay, to appreciate the fix, I feel like we really need to understand the broken tools first.
Definitely.
So traditionally, if scientists want to know what a chemical is made of, they rely on something called traditional infrared or IR spectroscopy, which is, essentially shining infrared light through a sample to get a molecular fingerprint.
Right, because every chemical bond absorbs very specific frequencies of infrared light. So the light goes in, and certain wavelengths are basically absorbed by the specific bonds stretching and bending. And then the light that comes out the other side tells you exactly what bonds are present in that sample.
Okay, let's unpack this for a second, because if traditional IR is so great at giving us this fingerprint, what's the problem? Why do we need a new tool?
Well, there is this frustrating physical barrier called the optical diffraction limit.
The optical diffraction limit.
Yeah, because light acts like a wave, right? And you can really only focus a wave down so far before it just gets completely fuzzy.
Oh, right. So traditional IR only really works on like a micron scale.
Exactly. And a micron is small. I mean, it's a fraction of the width of a human hair.
Sure.
But a molecule is thousands of times smaller than that. Plus, individual molecules have this tiny cross-section for absorbing that light. And on top of all that, the mid-IR detectors that we use are incredibly sensitive to ambient heat.
Oh, so they pick up thermal noise.
A massive amount of thermal noise.
Okay, so bringing it back to the rock concert analogy, it's like we can only hear the entire choir singing together. We're getting an ensemble measurement, but we literally cannot hear the individual soloists.
Right. You just get the average of the whole crowd. So you miss all the specific site signatures or, how one single molecule interacts with the atom right next door.
But wait, scientists aren't flying totally blind at the nanoscale, right?
Right.
I mean, we do have tools that can look at single atoms.
Oh, absolutely. We've had scanning tunneling microscopy or STM for decades.
Right?
STMs use this microscopic needle to measure electrons literally tunneling through empty space to map a surface.
Okay, so if we have a needle that can map a single atom, why didn't researchers just adapt that to, measure the vibrations? Like, use the needle as the microphone.
They tried. They developed these techniques called STM tiers and STM IETs to try and do exactly that.
But I'm guessing they didn't fully work.
No, they ran into some major fundamental physics problems. STM tiers, for example, relies on something called plasmon resonance.
Plasmon resonance. Okay, break that down for me. What is that?
It's basically trying to use the tip of the microscopic needle to trap and enhance scattered light. Think of it like trying to use the needle as a microscopic magnifying glass for the laser.
Oh, okay. That sounds complicated.
It is incredibly finicky. The signal depends heavily on the exact metal the tip is made of, its geometry, the optical properties of the sample. It's a mess.
And what about the other one? STM, IETS.
Yeah, so instead of light, that one tries to excite the molecule's vibrations by shooting electrons through it.
Shooting electrons? That sounds intense.
It is, and it creates terrible thermal broadening. You get this massive electronic static and really weak signals, especially at high energies.
Right, so it's like trying to listen to a super faint radio station,
Huh.
but your car's alternator is creating so much electrical interference that you just get a wall of static.
Exactly.
So traditional light is just too broad, and the previous atomic microscopes are too static-filled. We're essentially stuck.
We were stuck.
Right, so how did scientists figure this out? Because this is where the story gets really interesting.
This is where we bring in the masterminds. Dr. Xiaowei Li, along with the lead authors Kankai Liang, Zihao Wang, and their colleagues from the University of California, San Diego.
Okay, the UCSD team.
Yeah. In their 2026 science paper, they introduced this totally new machine called IRiSTM.
Which stands for Infrared Integrated Scanning Tunneling Microscopy.
You got it.
Wait, so they basically took a record player needle, the STM tip, measuring a tiny electrical current, and they just blasted it with a highly tunable femtosecond infrared laser.
That's exactly what they did.
That is wild. I mean, how does the laser not just melt the sample or blind the electrical sensors?
Well, it requires an extremely specialized environment. The whole apparatus is inside an ultra-high vacuum chamber, and then they freeze the entire system down to near absolute zero.
Near absolute zero.
Yeah, to run their first test, they put an ethanol radical, which is just a simple three-atom molecule, basically carbon and hydrogen. They put it on a copper lattice surface in a deep freeze at a staggering 7.05 Kelvin.
Oh, wow. So at 7 degrees above absolute zero, there's literally no ambient thermal energy. The molecule is just locked in place.
Exactly. It's essentially trapped in one of 4 specific positions on the copper grid, and then they hit it with the tunable IR laser.
Yeah.
They scan through different wavelengths, looking for the exact frequency that makes the carbon-hydrogen bond vibrate, which for ethanol is around 300-169 inverse centimeters.
Okay, let's pause there for a second. Inverse centimeters.
Oh, right. It's just a unit chemists use to measure the frequency and energy of light.
Gotcha. So when they tune the laser to exactly 300-169 inverse centimeters, what happens?
The ethanol molecule absorbs the light, and because it's trapped on this grid, the energy actually causes it to literally rotate between those 4 positions.
No way.
Yeah. It acts exactly like a tiny microscopic compass needle reacting to the light, and the STM tip hovering right above it reads the electrical change the second it moves.
That is so cool.
Yeah.
But how did they know it was the light actually causing the vibration and not just, I don't know, the laser heating up the copper?
Oh, they did a brilliant verification test. They took the ethanol molecule and swapped out the normal hydrogen atom for heavy deuterium.
Oh, right, because deuterium has an extra neutron, so it's heavier, but it's chemically identical.
Exactly. And if you have a heavier atom on the end of the bond, it's like putting a heavier weight on a spring.
It bounces slower.
Right, the frequency drops. And when they ran the test with deuterium, the required laser frequency shifted down exactly as the math predicted.
Okay, so they proved the machine works on a simple 3-atom compass needle.
Yeah.
But, real-world chemistry is messy.
Yeah, very messy.
So they need to test something more complex, right?
Yeah, so for experiment 2, they moved to a molecule called pyrrolidine.
Pyrrolidine. Okay, why that one?
It's a ringed molecule, and it's absolutely crucial for biology. It forms what's called the proline kink in protein folding.
Oh, okay, so it dictates how proteins fold up in the body.
Exactly. And pyrrolidine is essentially a shapeshifter. It exists in 2 primary shapes or conformations. There's a high state where the ring kind of puckers upward.
Like it's standing up.
Yeah, about 1.5 angstroms tall. And then there's a low state where it flattens out to about 0.9 angstroms.
Okay, so we've got a 3D ring popping up and flattening out.
Right. And when they hit it with an IR laser at 2.66 micrometers, it made the pyrrolidine rapidly shapeshift back and forth between those high and low states.
Okay, that is super cool. But wait, there was a twist here, wasn't there? The missing peak.
Yes. This is the real wow moment of the paper. So in traditional IR spectroscopy, the Quire measurement we talked about earlier, the absolute most obvious, loudest signal for pyrrolidine is the standard carbon-hydrogen stretch.
Right. It makes a massive peak on the graph.
Exactly. But in this new single-molecule machine, that massive CH stretch signal was completely invisible.
Hold on. The loudest singer in the choir just disappeared when we handed them a solo mic. Why? Does the physics just break down at the single molecule level?
Well, no, it doesn't break. It just works differently than we thought. They explained it using something called sudden vector projection theory.
Okay, sudden vector projection theory. Walk me through that.
Basically, the new machine only detects vibrations that actually cause the molecule to change shape. It measures structural change.
Okay.
The CH stretch definitely vibrates, but that specific motion just dissipates energy through the molecule. It doesn't actually distort the ring. It doesn't make it pop from high to low.
Oh, I see. It's like sitting in a parked car and just laying on the horn.
I like that.
Right, like you're making a ton of noise, you're expending a lot of energy, and everyone in the neighborhood or all the traditional IR sensors can hear you.
Yeah,
But you aren't actually putting the car in drive.
exactly.
To move the car, the laser needs to push the gas pedal. It has to target the specific chemical bonds that mechanically force the ring to pucker.
That's spot on. The loud, simple stretches were just noise. The machine acts as a filter that only registers the gas pedal. And because of this, they were able to use the machine like a chemical fingerprint scanner.
Oh, how so?
They placed 3 different isotopes of pyrrolidine right next to each other on the copper grid: normal pyrrolidine, pyro-ND, and pyro-D8.
Okay, and just to be clear, morphologically, under a regular microscope, these look identical, right?
Completely identical. You cannot tell them apart just by looking at their shape. But they tuned the laser to exactly 2034 inverse centimeters.
Gas pedal for the D8 version.
Right. And suddenly, only the pyro-D8 molecule started reacting and shape-shifting. The others just sat there.
Wow.
And then they tuned the laser to 2300 inverse centimeters, and the D8 stopped, and only the pyro-ND started twitching.
That is straight out of a spy movie. You literally scan a crowd with a laser, and only the specific secret agents you're looking for stand up.
It's exactly like that. They achieved in situ chemical identification at the atomic scale.
Okay, we need to zoom out to the big picture here. Because for you, the listener, you might be wondering, so what? Why should you care that scientists can make a microscopic ring twitch in a freezer?
It's a fair question.
So what does this actually mean for us?
It's all about the ultimate dream of chemistry, which is bond-specific chemical control.
Bond-specific control, meaning we don't just rely on mixing things and hoping for the best.
Exactly. For the longest time, creating chemical reactions meant heating up a whole beaker of chemical soup, right? An ensemble environment. You just add a bunch of heat and hope that the random thermal collisions break the right bonds.
Right, it's very blunt force, like cooking with a sledgehammer.
But now, with this platform, scientists can map and direct energy into a single, highly excited chemical bond.
Which means we can actually dictate the reaction atom by atom. That could lead to entirely new ways of manufacturing materials, right? Like custom building things from the ground up.
Absolutely. Technology, materials, science, the applications are massive. And then think about the medical field.
Oh, because of the purity.
Yes. Because it's that core structure in amino acids, understanding its exact physical constraints at a single molecule level helps us figure out the elementary steps in protein folding.
And protein misfolding is linked to so many severe diseases.
Right. Alzheimer's, Parkinson's. If we can elucidate how these molecules stabilize and fold at the atomic level, we open up entirely new pathways for medicine.
That is incredible. And I imagine this also affects things like catalysis for industrial manufacturing.
Big time. Most of our industrial manufacturing, from plastics to fertilizers, relies on surface catalysis.
Okay.
Uncovering these elementary steps with atomic precision will make those chemical processes vastly more efficient. We'll save energy and reduce waste.
Oh. So to summarize what we've uncovered today. First, the diffraction limit has officially been shattered. We can now actually take an IR spectrum of a single molecule by combining these femtosecond lasers with scanning tunneling microscopes.
Yeah, the impossible microphone exists.
Yeah, it exists. And second, we've basically discovered new rules of physics and chemistry here. We now know that only the specific vibrations that actually drive structural changes to gas pedals are the ones that matter for making a molecule shapeshift. The loud noise of the choir isn't always what's driving the reaction.
It's a really profound shift in how we view the nanoscale world. And I think it's a great reminder that human understanding relies entirely on the tools we build, you know?
Right.
By learning to see the invisible, we realize that the macroscopic world we experience, everything around us, is just the result of trillions of tiny, specific atomic dances.
That is beautifully put. And we'll leave you, the listener, with this to chew on as you go about your day. If this UCSD team can now identify, target, and manipulate the exact shape of a single molecule just by playing it the right microscopic tune of light, what happens when we start composing entire symphonies?
Oh, that's a wild thought.
Could we eventually play light like a piano to assemble custom medicines, or even like self-healing materials atom by atom?
I wouldn't bet against it.
Thank you so much for joining us in the Deep Dive Lab today. If you enjoyed uncovering this mystery with us, please follow and subscribe for more fascinating science stories that explore the hidden mechanisms of our world. Until next time.